Hey peoples, let's start learning for earning.
Welcome back to The Explainer. Today we're doing something really fun. We are going to translate some seriously dense academic robotics math into the gritty, physical reality of the factory floor. Because look, teaching a 6-axis robot to move from point A to point B seems incredibly simple, right? You just tell it where to go. But today, we're going to bridge the gap between textbook calculus and the actual physical movement of these massive machines. Okay, let's dive right into this. To really get how advanced robotics work, you have to realize there is a massive reality gap between our spatial awareness and how a robotic controller internally processes movement. You and I, we think in terms of forward, backward, left, right, perfectly straight lines. But a robot doesn't see lines at all. It literally only sees angles. It's basically a blind puppet trying to navigate a 3D world just by feeling the rotation of its own joints.
So let's look at translating this reality. Joint space versus Cartesian space.
First up, we've got joint space. Internally, the robot is only tracking the rotational degrees of its servo motors, usually joints 1 through 6. The total space of all these joint vectors, that's what we call joint space. The robot has absolutely zero inherent concept of up or down. But then on the flip side, we have Cartesian space. Some folks call it task-oriented space. This is the physical XYZ world with orthogonal axes that you and I operate in. So our entire challenge in robotics basically comes down to mathematically translating our Cartesian reality into the robot's joint reality.
Check out these overlapping realities on the arm here. You've got the world coordinate system, the base coordinate system, and the tool coordinate system all just floating in space. Now to us, drawing a simple straight line along the x-axis of that workpiece is, well, it's trivial. But for the robot, it can't just push one motor forward. To trace that perfect straight line, the controller has to constantly and perfectly synchronize the rotation of multiple joint angles, like J2, J3, and J5, all at the exact same time. It's this continuous, real-time mathematical balancing act. Which brings us to the core debate. Forward versus inverse kinematics. Take a look at this breakdown. Forward kinematics is essentially the where am I math. You input the angles of all 6 joints and boom, using direct trigonometry, the controller calculates exactly where the tip of the arm is in 3D Cartesian space. It's a direct mapping. Honestly, it's a lot like just reading a map. But inverse kinematics, wow, that is the how do I get there math. And it is vastly more complex. Think of it like trying to navigate a maze blindfolded. You give the robot a target Cartesian position, let's say x100, y50, z200, and the controller actually has to calculate backward through these complex, nonlinear equations just to figure out the required joint angles. And here is where it gets really interesting, and why we get system alerts like this. In forward kinematics, a specific set of joint angles gives you one exact position. Easy. But in inverse kinematics, we hit a massive real-world twist. There are often multiple valid joint configurations to reach the exact same XYZ target point. I mean, think about it. The robot could reach a point with its elbow up, or, with its elbow down. Since these nonlinear equations don't have just one simple closed-form solution, the controller has to rapidly evaluate the math and pick the most physically efficient posture in milliseconds. Otherwise, it might literally hit itself or the environment.
Let's bridge this to the factory floor, the tool center point, or TCP.
Because let's face it, out in the real world, a bare robotic flange isn't actually doing any work. We have to attach a tool. And this brings us to mastering the TCP. Step 1, you identify the special operational point on your hand or your grasped tool. Step 2, select a calibration method. And step 3, this is the magic part. We actually relocate all of our coordinate math away from the robot's default faceplate, moving it directly to the tool tip. Once your end-of-arm tooling is mounted, the robot needs to know its exact dimensions. That way, it shifts its entire mathematical center to the very tip of the welding wire, or maybe the center of a suction cup.
If you look at this teach pennant interface for a 3-point setup, you'll see fields for approach point 1, 2, and 3. Basically, the operator physically drives the robot tip to the exact same point in space, but from 3 totally different approach directions. And the trick here? To get a mathematically sound TCP, each approach needs a minimum angle difference of 45 degrees. The controller takes those 3 distinct joint configurations and calculates the precise XYZ offset of your tool.
Now here's a gritty factory floor secret. Imagine your robot is running this beautiful, perfect welding path, but then an operator accidentally bumps the torch. It bends by just 2 millimeters. If you don't catch this, the robot keeps flawlessly executing its math. But physically, it's welding thin air right next to the seam. But here's the thing. On the factory floor, you absolutely do not spend hours rewriting the entire complex Cartesian pad program. No way. You simply run that 3-point setup again, you recalibrate the TCP offset, and that invisible mathematical string automatically pulls the robot right back onto the seam. It's brilliant.
But what happens when things go wrong? Let's talk singularities, when the math breaks.
Okay, so a kinematic singularity is defined as a posture where the Jacobian matrix determinant mathematically approaches 0. Right. So what does that actually mean in plain English? Well, the Jacobian matrix maps the joint velocities to the Cartesian velocities. When it fails to be of maximal rank, which is basically hitting a mathematical gridlock, the end effector instantaneously loses the ability to translate or rotate in one or more directions. Honestly, it is an unavoidable hazard for literally any rigid link mechanism operating in 3D space. And when this actually happens on the floor, it is pure physical chaos. Imagine joints 4 and 6 aligning perfectly.
We call this axis collinearity. Suddenly, that inverse kinematics calculation we talked about, it attempts a division by zero to figure out how to move those aligned joints. Because the Jacobian fails to achieve maximal rank, the controller literally panics. The arm might lock up entirely and throw a massive fault, or, and this is terrifying, it might whip around violently, trying to generate an impossible acceleration just to escape the singularity. Even tiny motions in the immediate neighborhood of a singularity become highly compromised and totally unpredictable.
So what's the ultimate takeaway from all this? A robot isn't just a hunk of metal and servos. Mastering the machine, whether you are setting up a precise tool center point or trying to dodge a violent singularity, it all ultimately comes down to understanding the math. The kinematics, the Jacobian matrices, that constant relentless translation between joint space and Cartesian space. That math is the invisible string pulling every single twitch of the robotic puppet.
You know, it is basically a rite of passage for every programmer to crash a multi-million-dollar arm into a singularity. Have you ever hit one while holding a real teach pendant? I really want to hear your factory floor war stories. Think about how the robot reacted and what you actually had to do to jog it out of that locked state. Let me know your experiences, and while you're at it, tell me if we should crack open the incredibly complex world of robotic vision systems next. Until then, keep learning, and we'll catch you next time.
Let's study more, and like, share, and subscribe for such more content. And comment something you want to learn.